Okay, so today we will start a new unit, and the first topic in this unit we are going to discuss is regarding linear regression. Okay, and we will start with a single variable. Okay, so basically here what we mean, variable means a feature, single feature. We will start with this. Okay. And based on what we already learned in last unit, is about perceptron and add-line. And for perceptron, we discussed both the raw implementation and we also discussed sklearn. And both of them are used for classification. Okay, for classification. And for classification, that's based on discrete valued output. Okay, and in applications, a lot of time we also wanted to predict like real valued output or continuous. Value output. Okay, not like if it is this kind of flower or the other kind of flower, that then we can use, we call it a regression problem. Okay, but anyway, so over here it's also under supervised learning. And at the beginning, we also discussed the general 3 categories: supervised, unsupervised, and reinforcement learning. Okay, and over here right now, we discuss also supervised, and perceptron add-line are also supervised learning. Okay, then let's see. So we will theoretically, okay, see how the linear regression in machine learning, how we approach it to predict for real value output. Okay, and in our following discussion, we will use some notations. Okay, notation. So M then represent the number of samples, so training examples. And here is regarding training. And if you recall in sklearn that we also have that train test split, that so that's regarding your whole sample space. You're going to assign certain percentage for training and a certain percentage for training, for testing. So anyway, so over here, the notation M will represent number of training examples. And previously, we also learned, and X is regarding features. Okay, and here in math, we call them some input variables. Okay, and the Y is also vector, etc. And in machine learning, we call them target values. And here in math, you can also call them output variables. And the general idea for machine learning is you have some training sample set. So this is regarding data set. Is it? And then you apply some learning algorithm. So previously we learned is like a perceptron, add-line. Is it what today we will learn is linear regression. And more, is it? And the learning algorithm it will apply over here, we call it a hypothesis. So for linear regression, then we are going to, hold some hypothesis, is it? And over here you have the input, so the features, and you apply the learning algorithm to the hypothesis. Then you can estimate it and predict something, is it? And then testing. So over here for linear regression, here the example we are going to use is regarding like a housing price. Housing price. And for the housing price, then the feature we are going to, the single feature that here we are going to do the input is the size of the house, like the square foot. And the output is the price. We want to predict the price based on the size of the house. But previously we already see this single feature to predict a price will not be that the best model. That here we will start with using a single one because it also depends on other features. Is it like a number of rooms, garage, square foot, other features. Here we discuss linear regression, so estimated price based on the size. So this is also kind of continuous value, is it the real value? So we use the single features, okay, for our prediction to do the training. And then, so the hypothesis basically is just try to map the input to the output. So then I believe all of us know this quite well as a linear equation, is it? So this edge represents the hypothesis, is it? This hypothesis regarding some features. And over here in this case is the house size. House size, is it? So X is house size. And basically this theta 0, theta 1 is basically what we previously learned, the weight. It's the weights, okay. And this Y, then it is our over here. So we hypothesis it exists, this kind of relationship. Basically, this is our Y hat, is it? So estimated predicted value. And like this diagram also shows, so over here represent the sample points. Sample data points, is it? And here, this hypothesis. So this is that you try to find a best one using linear regression to predict like a kind of the trend. Is it? It's going to follow this hypothesis. Then whenever you have like a new house size, and then you can predict the price. So here is the price, then here is the size. So kind of, we try to find this pattern. But how to find this pattern? Is that there may be, because if you don't, so just like the perceptron at the line, is it? So this weights plays a very important role, is it? Because if you have different, then it can give you different line, is it? A different line. And so we can clearly say like this line, then it's off your samples a lot, is it? So how do we find the optimal one? This optimal one in linear regression. So this is regarding linear regression. Not the classification, okay, be careful, not the at-line classification. So this is regarding whenever then after you you find the optimal hypothesis, then you have some X value, then you can predict the respective Y value. Okay, that's the goal. And based on previously, if you recall, for the line, that we introduced the concept about cost function. So here, similar concept. Okay, we also try to use the cost function, and this is also similar as line. So our goal is to choose the weight. Okay, the weight, so that the hypothesis is very close to the real one. So this is a real target. Is it? And this is a predicted target value. We want to get in close this two value. This two, but here it's not a single one. It's you have a number of samples. Is it? So how do we optimize? Then here we try to find the offset. So this is offset because this is a data points. So Y value, a sample, is it? And this is your predicted one. And the offset then is going to be your predicted minus the real value. Is it minus the real value? So that's, and because it's over all of the samples, is it? And generally speaking, we also want to, so the offset also represents the error, is it? And here we want to use the sum of the square of errors, so SSE, is it? So over all samples, so that's why we sum of them up. Okay, sum of them up. And over here, we also, because it involves certain number of training examples, so we want to also divide it by double size of the training examples. And so the goal is to find the optimal weights so that we can minimize cost function. Okay, so minimize this value. So that's our goal. Okay. So we can, so theoretically, so here is all regarding math. Okay, so the cost function, generally cost function we write as J, is it? And cost function, be careful, it's regarding weights. Okay, regarding, so here basically, this is theta 0, it's the W. Okay, it's the W. And this value, it's a real value, is it? It has nothing to do with W. So this is known, basically in math, you can understand it as a known constant. And this hypothesis function, is it? This is a function of regarding weight, is it? And we try to minimize this cost function. And from math, you know, we already learned, if you want to try to minimize, you can take a derivative regarding W, is it? So you can take derivative regarding W and set it to 0, and then you can find the W, and then it will guarantee this cost is going to be the minimized one. So that's purely mathematical analysis. So here, let's take a look more. Okay, so here what we already explained is we hold the hypothesis. Okay, and over here, because it's linear regression. And be careful, linear regression is not regarding classification, okay? This is regarding continuous value, okay, target value. So we hold this hypothesis is it's a linear relationship, okay, regarding the predicted value and the features, is it? And the parameters here is weight. So basically it's our W, okay. And we define our cost function is sum of the square of error, is it? And over 2 times the number of samples. So our goal is to try to minimize the cost function. What is the optimal weight? And here just try to give us some intuition, okay? So if theta 0 is it is, so if W0 is 0, then we don't have the first term, is it? And we just worry about slope. So intercept is 0, is it? And in math, then you can draw a line, is it? Go through the origin, is it? And then correspondingly, this is the cost function. Is a cost function regarding W1, basically, okay? So it's a quadratic relationship. Is it quadratic? And we can clearly see, is it? So from 0, is it, for the weight, if you increase a little bit, then the cost is going to decrease at some value, is it? And then later, if you keep increase W, then the cost also going up. And here, our goal is to minimize the cost. So minimize cost clearly from this diagram, you can see this is the bottom. Is it? This is the bottom. So how do we find this? And from math, it's pretty simple regarding a single variable, is it, for the quadratic to find this minimum point. But we will approach it differently. So that's regarding a single variable. So W0 is 0, is it? But if W0 is not 0, so this is W0, this is W1, is it? And if both are changing, is it? And then this cost function is regarding 2 parameter unknowns. Is regarding 2 unknowns. Then if you want to draw, then that's going to be a 3-dimensional plotting. Is that you change 0 or W0, you also change W1, and then you can find the cost. Then the cost is going to be so 3-dimensional. Is that so? Here is W0, and here is W1. So here is the cost. Is that so? It's going to be the 3-dimensional, so all the point here. But even with this, we can see it's kind of like the bow shape, is it? So this is a bow shaped, and then all the convex. Is it contour plot? Okay, so this is the contour plot, 3-dimensional. And so over here, it's described the raw relationship, the hypothesis, okay, for linear regression. And if we want to draw it in 2-dimensional, so this is W0, this is W1, then for the 3-dimensional, certainly you cannot draw, is it? So the way is we do this contour drawing, is it? So all of the line over here. That means they have the same cost value, the same cost. And then this, the innermost one in this contour diagram, 2D contour diagram, this is the minimum cost value. Then you can find the corresponding W0 and W1. So that's our goal, try to find this point, is it? Okay, and then how do we do that? And if you recall previously, we also discussed gradient descent. Is it? So in machine learning, this is discussed a lot, okay? So gradient descent. So you can also directly doing math, is it, take a derivative regarding the weight, is it? But here we approach it in different way. We use gradient descent. So gradient descent, the concept is you start with some assuming, not the one that you know, because that's the goal. Those two are unknown, is it? These two are unknown parameters, is it? So we wanted to know those two values, is it? So we can assume it to start with some initialized value. And in our previous exam, like Adeline, we already see you start with some small value. Okay, and then we can keep changing these two. Is it? You try out, keep changing. And when you do the change, update, you need to reduce the cost. Okay, reduce the cost. And until you're getting very close to the minimum point, is it? And how do we decide? That means each time the cost update is very, very small, is it? Then you can assume, because it's already updated very small, then you can assume it's getting close to the minimized point, okay? So this idea, we call it gradient descent. But gradient descent, you said keep changing the weight, update. How to update the weight? Is it how? So that's a key step. Is it? That's a key step. So basically, it's you want your weight be updated. Those be updated. Whenever you update, that means this is updated value. This you add it. This is a previous iteration value. This is the current iteration value. Is it? And so the goal is to find this delta W. Is it the update of the weights? So how do we find it? And then we can. So that value is from, so you can take a derivative of the cost function. And here is partial derivative because you have multiple unknown variables, is it? So this is W0, W1, is it? And it's Wj, is it? And here J represent the features. So various features. So you take a partial derivative regarding different features, weight, is it? And then you time, so basically this is our previously learned, the learning rate. The learning rate. So you use the learning rate times the derivative of the cost function. is it? And you use the previous steps value, then minus. So this is our delta W. Okay, delta W. So we take a derivative of the cost function, is it? So it's basically regarding the respective. Get rid of this. That's okay, it's gone. Okay, so the idea is, so this part basically represent the delta W0 and delta W1. So the update parts of your weight. So update of the weight depends on what? It depends on the learning rate times the partial derivative of the respective weight. So this is how you find the weight. So we can also see the updates also depends on learning rate. So it also counts on learning rate. So how do we pick the best learning rate? Is it? So then we can, I remember previously we also see the example, is it? So the learning rate, suppose you draw a value. So here is a learning rate. Here is a cost function. Is it? So if your learning rate, is it? So it should be drawn like so. So some optimal value, of course, is it? But it must be like at a certain value you reach the minimum cost. As it reaches the minimum, and later if you increase the learning rate, then the cost will go up. As if it's too, so it also may be not a best choice, is it? So anyway, so also over here it's simultaneous update. Okay, update for both W0 and W1, and then you update and let it go to the next iteration. Okay. So that's gradient descent concept. And over here, it also explained, is that because over here, the cost function is quadratic, is it quadratic? So it's convex, bow tie, so bow-shaped. So it can approach from the left side, can also approach from the right side. Is it? No matter what, from both sides, you can always reach the minimum point. Okay, reach the minimum point. And also over here for the learning rate. So this is regarding learning rate. So if learning rate is too small, then the gradient descent will be slow, okay, for the updates. So that's obvious, is it? And if it is too large, then it can cause overshoot the minimum point. So it may miss the minimum point. Is it? If that's the case, then it will fail to converge or even diverge. So we don't want it too slow, and also we don't want it to do the overshoot. Okay. And also over here, it also discusses the gradient descent. It can also converge to local minima, not a global one, is it? So like in this diagram, so this is the global minima, is it? And if you start at like this side, is it? Then you reach to this point. So this is called local optimal point. And also we don't need to worry, okay, it's as we approach to local minima, the gradient descent will automatically take smaller steps, okay? So there is no need when we do the number of iterations that we call it epochs. Is it? So we don't change, okay? So no need to change learning rate. Okay, so keep this in mind. Okay, for gradient descent, so the key point we need to remember theoretically, okay, is okay, linear regression, that's the model, the hypothesis, is it? And here is the cost function. So cost function is regarding weights, always keep that in mind, okay? The linear regression is regarding what? Regarding feature, okay? And the goal is try to minimize cost, okay, minimize cost. And how do we minimize cost? Then we can take a derivative of cost and let it times the learning rate, and then keep updating the weight, and then the weight will reach to a certain point. Is it? So when the weight updates is very, very small, then you can consider it to converge. Or you first define like maybe 100 number of iterations. If it didn't reach the threshold that you define for the update of the weights, then you also let the iteration stop. Okay, you consider it as conversion. And as to how to take a derivative, and I believe all of you already know from math, is it? Because this is a hypothesis function, is it? And you just replace it with the hypothesis function, is it? And then you take a derivative regarding theta, is it? So if it's regarding theta 0, then only this one is unknown. And all these parts are known. Is it? And when you take derivative, so from calculus, you know you can come up with this result. Okay. And the same thing for W1, is that you can also come up with this expression. Okay. So that's very obvious. So from calculus. Okay, so here is just give us more detailed description about gradient descent algorithm. Okay, it's just update both W0 and W1 simultaneously using this formula. Okay, using this formula. And using this formula, this is the real targeted value, is it? And this is the hat one, is it? So predicted ones. So we know both, is it? We know both. And this value, we also know, this is feature. Feature, we also know, is it? So that's why you can keep calculate this, is it? And then you can keep updating the weights, is it? And then we can find the optimized weights for our goal. And previous we already saw quite a number of times for the cost function. Okay, so anyway, cost function, be careful here only regarding linear regression. So it's a convex function or bowl-shaped function, is it? And in this case, it has a global minima, is it? Because it's just that one point. And also regarding what we just discussed here, what we discussed here, if you take a look, when we calculate the gradients, is it? We consider, because M over here is number of training samples. And here we take, we consider all of them because we sum up all of them, is it? So this idea, then we call it batch gradient descent. Okay, so each step of the gradient descent calculation, we use all training samples This is called batch gradient descent. Okay, in another one, it's called stochastic gradient descent. Then it doesn't use all. Each time it just use one sample. Then that's called stochastic. Okay, or it's also called online learning gradient descent. Okay, this is batch. We can consider as offline. So that's the concept. And later on, we will discuss this more, okay? So anyway, so this not just apply to regression, it also apply to classification. We call it cross-validation, okay? What cross-validation, the idea is, if you recall previously, we already discussed, is it the sample space, you divide it into training and testing. Is it training, testing? And here cross-validation, and we can do further dividing, okay? So in this case, you also divide them into, suppose like 4, we call it folds, 4 folds. So this is a fold, so 1 fold. And the second fold, third fold, the fourth fold, is it? And then how do we train the model is we can pick. So in this case, you pick the first 3 folds. You pick the first 3 folds for the from the training, okay, from the training, is it? And then you use the last one, is it, for the testing, okay, for the testing. And then you can, next you change 2, 3, 4. You use it for training, is it? And the first one, you use it for testing, is it, for testing? And so you pick the different combination of the folds and using one of it. So one of fold serve as testing, is it testing? And the other 3 in this case serves for training, okay? And then for each of this, the result will be different, is it, the training result? And what we can do is you can average all of the errors together, is it? So this kind of concept, we call it cross-validation. So here just give you a glimpse, and later on we will discuss more in detail, okay? And what is the next part? We are also going to discuss the polynomial, okay, case. And so generally speaking, okay, generally speaking, if you try to use the polynomial model, okay, so in this case, like we have the single feature, that single feature is the house size. And for linear, then it's just, so here is your sample data, is it? You can kind of see it's off quite a lot, is it? So the idea for the polynomial is, can we find some curve? Is it a polynomial? So this is polynomial expression, is it, to represent the relationship between the features and the predicted values. Okay, then in this case, the house size, then it depends, it's maybe the first order, then the second. So you quadratic the house price, or cubic, or you take a square root, is it? polynomial model, okay? But you still just have a single feature, is it? Then you may say, okay, is it the more complicated the polynomial model it is, then the better the performance will be? It's not always that case, okay? Because later on we will also see, okay, so here, then you can kind of like also consider the relationship between the degree of the polynomial, is it, versus the error, is it versus error? Then you can clearly see it may also follow this kind of trend. And this kind of trend, so this is considered as the best fit, is it? And so with the increase, looks like if you increase in polynomial terms, the orders higher, is it? It kind of, okay, getting better, is it? But below the best, then the error rate is high, is it? So we call this underfit. And if you increase, so you make your polynomial model quite complicated, then you will also find some problem is the training model fits very well, but the performance will be bad for real testing. Then in this kind of case, okay, we call it overfit. Okay. So this is the concept regarding underfit, overfit, and of course, it's just not regarding polynomial. Okay, quite a number of parameter tuning can impact underfit and overfit. And what is the next one? We have discussed previously. We discussed linear regression with single feature. Is it? But that's not in the real world case, is it? In the real world, you have multiple features, is it? So like a number of house, or number of rooms, square foot, garage, is it? All sorts of features you should consider for housing price prediction, is it? Then in this case, we better using multiple variable, is it, for linear regression. Then it can be represented as this format. So here you have n features, from 1 to n features, is it? And in math, then you can represent as vector formatting, is it, like this? Okay, so that's so in vector formatting, then you can still write like this. Is it, you transverse the weight vector, is it, and the times the feature vector. So this we call it multivariate linear regression. Okay, regression. And for multilinear regression, and for the weight, okay, the weight vector, then it's n+1 dimension. Be careful, okay? And that's why, because we have this, if you recall, bias term. Is it? Because in this case, x0 is always 1, is it? And then this is the interception, is it, theta 0, w0. Then we call it bias, okay? And for multivariate linear regression, same thing for the cost function, okay? We still take the sum of the square of error and divide by 2 times the total number of training samples. So the concept is still the same as singular linear regression, okay? And for gradient descent, then it's the same thing, it is simultaneous, okay, for all of the features. So you can just repeat with certain number of epochs, etc. So similar. Then you take a derivative for each of the weights. Okay, and here it also explained for gradient descent. If you recall, in our example, we also discussed feature scaling. Is it in sklearn? It provides us with the standardization feature scaling, etc. And in this example, why we need a feature scaling is like the size. That house size is like in the 1,000 range for the square foot. Is it? But for number of bedroom, normally it's 1 to 5, something like this. Is it? And if we don't do scaling, is it? Then regarding like the weight, is it? And here is the cost function. So this is the contour for cost. Is it? Then you can see it's skewed. Is it skewed? Then it may take a long time to converge to the global minima. Is it today? And if we try to scale it in this case, okay, because the square feet is arranged in the range of 2,000, then you divide by a number of them, you divide by, then it can bring both features to the scaling 0 to 1. Is it? And because they are pretty close in the same scaling range, is it? When we draw the cost contour, then it's not that skewed. Is it? So it can expedite the gradient descent conversion to the global minimum. Okay, so that's why we do feature scaling. And the feature scaling, if you just do the range, is it? You can just do the range. Is it? And also we call it mean normalization. Is it? And you use the mean value, is it? And divide by the range. Okay. And we can. So generally speaking, the goal is to bring the range to -1 to 1. Okay, so that's on the same scale. And for the sklearn, it use so over here. So this is a mean value, average value, and you can also do the standard deviation. Okay, so that's or you can do the range. Okay, you can do the range. So that's for the feature scaling. And learning rate. Okay, learning rate is recommended to not use too large a learning rate because it can cause what? Overshoot. Overshoot, then it may miss the minimum point. Is it minimum point? So you can choose some smaller learning rate. And how can we like make sure the gradient descent is working properly? And then you can plot the cost, is it? The cost function and the number of iterations versus the number of iterations. So if the cost is decreasing, is it? If the cost is decreasing after each iteration, then you know the learning algorithm is working appropriately. Okay, so that's the goal. Okay, that's the goal. And then You can also declare how to converge, is it? Because the best converge is 0, is it? But that's very hard to reach, is it? So you can declare the converges, the cost decrease by less than certain value, is it? So over here for each iteration that you say, okay, it's less than 0.1%, is it? Then you consider it's converge. And if your cost and the number of iterations, the relationship is going up, then definitely it's not working, the gradient descent, okay. And here it's using smaller learning rate, that so for sufficient small learning rate, the cost should decrease on each iteration. But of course, if you pick too small, that's also not preferable. Because why? Because then gradient descent can be very slow. Okay. I think we already run out of time today. Okay.